All right, welcome to the deep dive. We've got some really interesting material here on scaling up experimental validation for AI in computational catalysis.
Yeah, it's a fascinating area. We're trying to speed up finding catalysts, for big challenges like green hydrogen and CO2 conversion, stuff that really matters for climate change.
Absolutely huge stakes. And these sources really dig into, well, the core problem,
Mm,
the gap between AI predicting a great catalyst and actually, making it work in the real world.
exactly that. It's the bridge between the computer simulation and the lab bench. And that bridge, well, it's pretty shaky right now, especially on the experimental side.
Right, the synthesis. The papers focus on these ordered intermetallic nanoparticles, which sound particularly tricky to make.
Oh, they are. Synthesis is a major hurdle. You're trying to create these tiny particles like nanoscale Legos where every atom has its specific spot. That order is what makes them work well.
But getting that perfect structure,
It's incredibly difficult. Getting the right size, making sure it's just one single crystal phase, not a jumbled mess, and keeping that atomic order. Yeah, failure rates are pretty high. It's just part of the game at the moment.
so how did the researchers in these studies actually try to make these materials? What were the approaches?
They use two main methods, kind of complementary ones. First, chemical reduction. That's a wet chemistry approach. And interestingly, they used an automated robotics system for it.
Okay, robots in the lab,
Yeah.
already pushing the automation angle.
Definitely. The second method was spark ablation. Totally different. It's a dry technique. They basically zap metal rods with sparks to create nanoparticles, like a kind of additive printing almost.
There's flying. And using both gives them access to different types of metals and alloys.
Yeah, different elemental combinations are easier or harder with each method, so using both broadens the possibilities.
Okay, so you try to make these complex things, but then the crucial step seems to be figuring out if you succeeded. Verification.
Absolutely critical. That's where characterization comes in. It's the essential link, between the ideal model on the computer and the messy reality of what you actually synthesized. Without it, the prediction is just theoretical.
And the sources highlight two key techniques they use for that.
That's right. First, X-ray fluorescence, XRF. That tells you what elements are in your sample and roughly how much of each. The composition.
Okay, so element check. And the
Or
other,
X-ray diffraction, XRD. This one gives you the structural information. Did you get the right crystal phase? Is it ordered like the prediction said it should be?
got it. So XRF for what's in it and XRD for how is it built.
Exactly. And using both lets them filter out the duds, wrong composition, multiple phases, wrong structure, and focus on the samples that actually match the target. Oh, and they did this on silicon wafers, which is smart. Avoids confusing signals from the substrate.
Right, clean data. So
Yeah.
synthesize, characterize, filter. Then how well did the AI models actually predict the performance once they had these validated samples?
Well, they built models using computational data, things like how strongly molecules stick to the surface absorption energies. For simpler reactions like hydrogen evolution, HR, they found some okay correlations, not perfect, but usable.
But the big one, CO2 reduction, CO2RR.
Much tougher. The models struggled more there, especially predicting results for completely new compositions the AI hadn't seen before. The correlations were just weaker.
Suggesting the current ways of describing catalysts computationally aren't quite enough for that level of complexity.
Pretty much. It seems we need better descriptors, better ways to capture what makes a catalyst good for CO2RR. But there was a really remarkable finding for her.
Oh, what was that?
Even though the models weren't perfect, a purely data-driven analysis, looking at the experimental results, it actually pointed to platinum PIA as a top performer for her.
Okay, but platinum is known to be good for her, right?
Yes, but here's the kicker. PD-containing alloys weren't in the training data they used. The patterns in the other data were strong enough for the analysis to independently flag p-Tau-key.
Wow, okay, that is pretty wild. So even if the models need work, the data itself holds huge potential.
Exactly. It's a powerful glimpse of what data-driven discovery could do.
Which leads right into the future directions, doesn't it?
Yeah.
What do these studies suggest we need most urgently?
The absolute key insight, and this jumps out from the material, is how model accuracy scales with data. It's a logarithmic relationship, much like we see with large language models. Basically, small increases in data give diminishing returns. To get big improvements in prediction,
You need way more data.
vastly more. We're talking potentially needing data sets in the order of 10,000, maybe even 100,000 materials, all experimentally validated.
10 to 100,000. Right. Compared to maybe hundreds in a typical study now,
Yeah.
that's a massive leap.
It's huge. And building experimental data sets that big, making sure the data is high quality, reproducible, covering diverse materials, well, that's incredibly expensive and difficult right now. Synthesis and characterization at that scale. That's the real bottleneck.
So summing up this deep dive then, bridging the AI experiment gap really comes down to needing enormous, high-quality experimental data sets. But making those data sets is the massive challenge the field needs to solve because current methods are just too slow and costly for that scale.
You've got it. That's the core tension right now. We know we need the data, but getting it is the hard part.
It really makes you think. Given that almost unimaginable scale of data required tens or hundreds of thousands of experiments, how might the scientific community need to, perhaps, fundamentally change how it collaborates or automates just to even approach building data sets like that?